In this lecture, today's lecture, we're going to talk about the concepts of probability and distribution using some sort of a statistical tool called Galton board. Galton board is a toy which had been, or the demonstrator, which had been invented by a mathematician. We will use it to understand the concept of probability and distribution, and we will talk about a little bit about binomial distribution using that example. Galton board is actually a board, wooden board, made of a plank of wood and some nails stuck on it, as having the pattern as shown here. It's held vertically, and you roll down or drop a ball or metal ball, small ball, as shown here. And as the ball hits the nails, it either goes left or right. In this situation, the probability of going the ball to the right and left is exactly the same, equal. So 0.5. The probability of going it to the left or right is 0.5. And as it goes either to the left or right, it sticks to the next nail, and again it goes either to the left or to the right with equal probability. And it continues its way down to the bins shown with the red squares lying at the bottom of the array of nails. Okay, as the probability of a ball or marble choosing any path is just random. If we drop many marbles and repeat this experiment many times, are we going to end up with a situation where the number of marbles in each container being more or less equal? Let's investigate this a little bit in detail. For the marble to end up in this container, it can take one of these paths shown here. So it can go from first to the left, then right, left, and so on and so forth, shown with the red arrows. If it follows this path, then it will end up in the container shown there. To fall into the container on the far left, it can only take one path, though. It has to do left, and end up in the far left container. However, when you look at the other container, to get there are multiple ways to the marble can follow. Only 3 of them are shown here, and they are shown in different colors. For example, the orange path, the green path, and the light blue path. They all lead to the same box, to the same container. However, for the extreme left container, there is only one path. So, what is the number of paths that lead to a container? The easy way to calculate it is using Pascal triangle. Pascal triangle is named after the French mathematician Blaise Pascal. However, it's not his invention, although he made it popular. Pascal triangle is shown here, and to get this triangle or to construct this triangle, what you have to do is you start with a 1 at the top, and then you put 2 1s as shown there, and you put addition of those 2 numbers in the row just below them. So 1 plus 1 makes 2, and then you write 1s on the right hand side and 1 on the left hand side, and then you add up the adjacent numbers and you write the sum onto the row below. By using this procedure, you can construct this triangle. As you can see, 6 plus 4 is 10. You write 10 on the row below that the row which contains the 6 and 4. So on and so forth. You can enlarge this triangle as much as you can. So this triangle is actually telling you the number of ways, different paths you can follow to get to a certain pin or this certain point on the Galton board. You can go back and think, why is this the case? This is the case. Of course, it's obvious, but I'll leave it to you to find the reason for this. So, if you look at the pin that's circled with the red circle, you see that the number is 10. So there must be 10 different ways, paths, to get to that point from the uppermost pin. What does it tell us? They tell us that to get, for example, to the container numbered 5, there are 35 different ways to get there. Why I'm saying 35? Because there are 2 pins you have to hit before you drop or get into the container numbered 5. And as each pin, with a probability of 50% chance, let's say, of when you get to one of those pins, you have a 50% chance to fall into 5, or 50% chance of falling either into 4 or into 6. So there are 2 pins in this position. There are 35 different ways to get to the bin numbered 5. Okay? So to get to the bin in number 3, you have either have to hit the pin 21, number 21, or the pin numbered 7. But only half of those will end up in 3, so you have to add these 2 and divide it into 2. So 28 divided by 2 is 14 different ways to get to the bin numbered 3. Like this. Okay? So let's ask the question again. What will be the distribution of the number of marbles in these containers if you repeat the experiment we did at the beginning of the lecture by dropping the pin, by dropping the marble on top of the first nail? Will it be something like this? Will all the containers end up with the same number of marbles? If we did this experiment with multiple marbles, we'll end up something like this. I will put a YouTube video link in the lecture, under the lecture video, so which shows an actual physical Galton board at work. So I recommend you to go and check that video to see the experiment by yourself. Why is this the case? Why the bin at the middle gets the most marbles, and as you go to the edges, the number of marbles declines? What's the reason for this? First of all, let's introduce some concepts or definitions. The number of marbles in each vial or container is called the distribution, and each drop of marble we executed is called a trial. So we did many trials here, and the outcome of these trials constitutes the distribution. And here it's a binomial distribution because the reason for this is that the probability of a marble falling either to the left or right is equal. The probability is 0.5 or 50% chance of it's going to the right or left. So this gives us a binomial distribution. It can, in other cases, can be different. I mean, the probability of going to the right and left can be different. So it will give us a different distribution. Here, it's because of this 50-50 chance of going either right or the left, this is a binomial distribution. And the average of this distribution, the average that you learned in your high school years, is the expected value of this. It's called the expected value of this distribution. What is that expected value of the? Let's calculate it. Actually, the number of ways you get to a container times the value of that container. Let's say that the value of the container, each container, is the number of the container. Less that the left container has the value of 1, the second one has the value of 2. So if a marble falls into 2, the marble has the value of 2, let's say. Okay. So if we multiply this number, the value of this each container, and multiply it with the number of ways, paths you can follow to get to that container, and add them up together, and divided them by the total number of paths you can follow in this triangle, you'll end up with the number called the expected value. But this is a theoretical value. It's not necessarily the value you get when you do a set of limited number of trials. Say you drop 5 marbles or you drop 10 marbles. You may not end up with that number. If you have a limited number of trials, you end up with different distributions. And you end up with different expected values. So the number we're talking about, the number of 5 we're talking about, is a theoretical number. We'll come to that. What it means, we'll come to that. Okay. Actually, what is the connection between this toy and the binomial distribution? We can imagine it like this. Say each row is a trial. So every time you flip a coin, it's similar to a marble hitting a nail here. It either goes left or right with equal probability. It's similar to flipping a coin. It's either come up head or tail with equal probability. If it goes left, we'll call it tail. If it goes right, we'll call it head. Okay? So let's see. The first flip will be tails. The second flip will be tails. Or third flip can be tails. Okay? Or you can have tail, head, tail. Okay, that's it. So we did 3 trials, or we flipped 3 coins at the same time. So the thing is, to get to this point, you need 3 tails in total. There's only one way to get to this point. You have to flip 3 times tails. Okay, to get to this point, shown with red, you need 2 tails and 1 head. And to get to this point, shown with red, you need 3 heads in total. And this is in total. The sequence of heads and tails is not important, because you can either get to the point shown here with tail, head, tail, or you can get it with tail, tail, head. It doesn't matter. Head, tail, tail. It doesn't matter what's the sequence. of the heads and tails are. The important thing is the number of heads and tails. Here it's important. The sequence is not important. The number of heads and tails are important. Okay, so the similarity between the Galton board and the flipping coin experiment is obvious, I believe. So let's see what will be the distribution. So what is this path corresponds to? It means that you have 6 coins flipped, or you flipped a coin 6 times, and you end up with tails each time. Okay? This means that if you flip the coin 6 times here, and you flip tails each time, you'll end up with the average value of heads will be 0. Because you throw 0 heads, you throw all of them tails. Say, if you each throw, if a tail comes up, you say 0, and you if a head comes up, you say 1, and you sum up all these values and average them, you'll end up with 1. In the case of tail, all flips ending up with tails, you end up with an average 0. If you end up with half of the flips with tails and half of the flips with tails, your average number will be 0.5. Okay? So if you increase the number of trials from 6 to 10, you see that the number of paths you can get to the 0.5 average is 252, but to get to the the number of paths you can get the average number 1, which means all flips will be tails, is only 1. If you continue to increase this the number of trials, the number of rows on the Galton board, in a sense, the number of paths to get to the 0.5 average will increase. As you can see from here, from 20 to 252 it increased. However, the number of paths going to the 0 average or 1 average, which means all heads or all tails, stays the same. It's only 1. It's always 1. So the difference between these two averages, the number of ways you can get to either to the center pin or to the marginal pins, gets even larger and larger. The difference gets larger and larger. So you have much more ways to get to the center point than to get to the points to the far left or far right. If you increase the number of trials, this difference will increase even further. So it tells you that if you do this experiment, do these trials many times, so it's very unlikely to get to all heads or 2 tails, but you're most likely to get to 0.5 average, which means half of the flips will be heads, half of the flips will be tails. You can see it here. If you throw 5 coins, if you try it 5 times, so throwing 5 heads or 5 tails in a sequence is not very unlikely. It's not very likely, but it's not impossible. So you end up with averages 0 or 1. Less likely than getting a 0.5 average, but you get still can get an average of 0 or 1. However, if you start to increase the number of coins you're flipping, it's getting less and less likely to throw all heads or all tails. As you can imagine, throwing 100 tails one after the other is very, very unlikely. So the distribution starts to collapse. So you most likely to end up with 0.5 average. You have to understand that this distribution itself, the number of k times you end up with the percentage of times, let's say, to end up with an average 0.5 or an average of something. If you do this with 5 coins once, you may not get this one. You may end up with all heads or all tails time to time. That's true. However, if you repeat this experiment many times, I mean, if you throw 5 coins many times, and then you put the number of times you get 0.5 average, the number of times you get 1 average, number of times you get 0.17 average, and things like that, you will end up with this distribution. Okay, this is called the law of nudge down, which means that if you repeat an experiment many times, you'll either end up with the theoretical distribution, or you'll end up with the theoretical average value. So this is a very brief introduction to concepts of probability, distribution, and a little bit binomial distribution. See you next lecture.